Wanted to give you an example of how you can find a least squares function for a set of points. So this one asks for the least squares quadratic for this set of 8 points. So remember that a quadratic function means that we've got an ax squared plus bx plus c, and in order for the least squares part to work, we need a system of linear equations. What we're trying to find are the a, the b, and the c, so we really do have here a linear function of the coefficients. Each of the coefficients is, that's what I mean by the function is linear in its coefficients. We're going to plug numbers in for x. So I have just an ABC. That's a linear equation that we'll have. All right, so the first thing we do is we set up our equations. The way we set up our equations, again, is to plug in the x value into the function and set it equal to the output that it needs to be. So we notice, just to go through the first one, you plug in -3 for x, you get 9 times the a, you get -3 times the b, and you get 1 times the c. So that's equal to 7. And you should be able to go through and verify that those are the other 7 equations that you would get just by plugging in the x values and setting them equal to the corresponding y values. It's not too hard to see right away that this system of equations is not going to be consistent. Look at the second and third equations. They're definitely not going to give you the same, or excuse me, these are never going to give you a solution because you've got the same exact expression on the left-hand side equal to 2 different numbers. So this is definitely not going to be a consistent system, which means, again, that we've got to make our best solution possible in that least squares sense. All right, so now I need to solve this, and we need to set up, figure out the solution to the normal system. So in this case, the coefficient matrix is just pulling off the coefficients on the a, b, and c, and the vector b that we have is, of course, the constants. All right, so we know that how to compute our least squares solution. So the first thing we're going to do is calculate our A transpose times A. So this is a great job for a calculator. We get this matrix. Again, remember that when you do A transpose A, that's always going to be a symmetric matrix. So we really do see a symmetric matrix here. Also, it's going to be invertible as long as we have linearly independent columns of our original matrix. There are 3 here, and it's not too hard to see these are going to be linearly independent. It's also not hard to see there's going to be linearly independent when we had that inconsistency issue. We're not going to be able to have, issues here with this going to be not linearly independent across the columns. All right, so we know the least squares solution is given to us by this. So we just plug in the different pieces. This is A transpose A, this is A transpose, this is B. You go through that, you probably get decimal approximations on your calculator when you do this, but those are the fractions. Like I said, computer algebra systems are wonderful things. So this is what the solution would look like if you had fractions. So here is your least squares quadratic. So just to give you a picture of what this looks like, I'm going to cover up a little bit of that matrix above, but notice the dots here are your different points. That just plotted those points in there, so you can see the 8 points again. And you can see the curve gets close to some of them. Kind of looks like it goes through a couple. Not really, but close to a couple. This one, it misses by a pretty good distance, but notice by this one's how far away it is from this one. We're getting made up by this one and this one over here. So this is your least squares quadratic from that particular set of data. So just wanted to give you an example and then show you a picture that goes along with the ideas that we've been talking about.